Welcome back, 6th grade students. We are taking a look at our week 7 Bellwork / homework, which is due Friday. So remember, this assignment is assigned every Monday and Tuesday of the week. You have all week to be working on it, and it is due on Friday to your core math teacher. I'll take a minute and run through these problems with you. Maybe you ran into one or two at home that you struggled with and you want to fast forward and just compare answers. Maybe you want to see what strategy I'm using. Pause my video, think through the steps, and then compare when you're done to see if we have the same result. So taking a look at the first problem here, it says use greater than, less than, or equal to solve the inequality below. It's an inequality, so I'm thinking to myself, I'm going to do some comparing. Well, I noticed that on this problem we're fortunate to have the same number of parts in our denominator. Both of these are split into tenths. So if I really wanted to prove my work for my core math teacher, I might draw two bar models. And this would be a comparison bar model. I'm drawing two different bars. That second one is really questionable, but we're going to make it work. And I would split them both into how many equal parts? 10. So to get 10 equal parts, I need 9 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. Not perfectly judged, but not too bad. And I'll try to bring these straight down, so at least our parts can be compared pretty quickly. And if I do those 9 lines, I should end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equal parts, or as close to equal as I can make them in a quick sketch. Next, that represents my denominator, but I notice that the numerator says I have different amounts. So in the numerator, I have 8 shaded pieces. Maybe I have 8 tiny little pieces of my candy bar left. So I'm going to shade in 8 parts to show that. 8 parts of the whole. For the second fraction, I have 5 tenths, or I only have 5 of the total 10 parts. So I'm going to shade in just 5 little pieces. Using this bar model, I can see that my favorite candy bar, I hope, is this top one, because it looks to me like it ends with more shaded than the bottom bar. So for that reason, the first fraction must be greater than the second. Notice we did not have to deal with common denominators or finding a common denominator, because we were lucky enough in this problem to already have tenths and tenths. There was already a match. So we didn't have to change it to 20ths or hundredths or anything else crazy. We were able just to use what was there and really look at those numerators. A bar model is just helpful in seeing that when I shade, I end up with more parts or more shaded in the first fraction than in the second. Next, I'd like to look at this next problem with you. It says find the product. Let's see if I can find the product and scroll to that next problem. I think the first thing I'm going to show you is an area model. So I think some of you have seen this in the elementary. This is a really nice strategy if maybe you don't remember how to handle multi-digit multiplication. So we kind of break the numbers into pieces. So this 7,263 is the same as 7,000 plus 200 plus 60 plus 3. Some of you would remember that being called expanded form. And then I could break this 27 into 20 plus 7. If I were to try that in an area model, I will try that off to the side. I'm afraid I might run out of space, but I'm going to give it a go. I'm going to have that many pieces, 1, 2, 3, 4 parts in my area model. So I'm trying to think if I'll be able to even fit this in here. 4 parts running across the top to represent my 7,000, my 200, my 60, and my 3. And then just 2 parts running the other direction to represent my 20 plus 7, or 27. Well, now I really want you to rely on your number sense and knowing what happens when we multiply by tens. So if I take a look at this first intersection, I have 7,000 and I'm multiplying it times 20. Well, I'm going to ignore my zeros for a quick minute, and I'm just going to say I know 7 times 2 is 14. But I want you to take a look. How many zeros do you see at the back here? Hopefully you would say 3 from the 1,000 and 1 from this 20. So 3 plus 1 gets me 4 zeros. I'll get 140,000 just from that multiplication. The next step I would look at is maybe an intersection of 20 times 200. Well, again, I would take my first leading numbers and I'd multiply that 2 times 2 to get 4. And I'm going to use my tens rule to know that if I multiplied 2 groups of 10 times another group of 10, I get 3 groups of 10. I probably shouldn't have said 3 groups of 10. It's 3 place values of 10. So I'm going to end up with 4,000. I have 3 zeros in my answer. The next intersection shows me 20 times 60. So I'm really going to take those leading numbers at 2 times 6 to get me 12. And then using this rule of tens, 10 times 10, I have a 0 here and a 0 there. It's going to get me 100. And 100 times 12 gets me 1,200. Or I get those 2 extra zeros at the back. 1,200, 4,000, and 140,000 so far. The last intersection I see is this 20 times 3. And here again I would take 3 times 2 to say I get 6. And I would remember that when I multiply that by 10, one zero at the back, I'm going to see that in my result as well. I'm going to get a product of 60. Alright, we've taken care of 20 times all of those parts. Next we need to do the same thing with the 7. So 7 times 7,000 is the same as 7 times 7, which is 49, with how many extra zeros? 1, 2, 3, to make sure we get to the thousands. Next I have 7 times 200, and I know 7 times 2 is 14. How many extra zeros would I have back here? You might notice that there are 2, so I'm multiplying that by 100 to get 1,400, or 1,400. Next I have 7 times 60, and 7 times 6 is 42. And I have that extra 0 at the back. It's like multiplying it by 10. So I'm going to end up with 420. And last but not least, 7 times 3. This is one that my students don't love to remember, but we'll try it anyway. Let's count by 7s. 7, 14, 21. I'll get 21. Now this area model, it's not really drawn to scale, but it is really nice because it gave me a lot of chunks and a lot of zeros that will kind of make my job nice. So I can take all of those pieces and I can total them up. I can take the largest product I have here, the 140,000. I can take the second largest product I have here and stack it up. And again, the order wouldn't really matter because we would say addition is commutative. It can be rearranged all day and all night and you'll still get the same awesome result. And notice I'm just taking the products. This is called the partial products approach. It's pretty entailed because there are so many different pieces, but sometimes that cuts down on errors with all the regrouping that students experience otherwise. So to find a total product, I'm going to add these all together. All these zeros in the ones place, plus 1 gets me 1. All these zeros, plus 2, plus 6, plus 2. Let's see, 6 plus 2 is 8, plus 2 more is 10. I'll keep a 0 and regroup that 1, showing another group of 10 moving to the next place value. Here I have 1 plus a lot of zeros and a 4 makes 5, plus 2 more, 6, 7, plus 4 more, 8, 9, 10, 11. I get 11. I'm going to keep a 1 and regroup that new group of 10, trade it in for a group of 10. Now I'm going to add up here in the thousands place. 1,000 plus 9,000 gets me 10,000, plus 4, 14,000, plus 2 more, 15, 16,000. I'm going to keep the 6 in the thousands place, and I'm going to regroup that 1 to the 10,000s place, one group of 10 moving over. Here I have 4 plus 4 in the 10,000s place. So 4 plus 4 is 8, plus 1 more is 9. I end up with 9 in the 10,000s place, or 9 10,000s. And last but not least, I have 1 plus nothing, so I could just bring that down. That 1 is in the 100,000s place. That's going to land somewhere in here near this dark line, isn't it? For a final answer, I would move over 1, 2, 3 places to help me read this. So moving 3 places from the right towards the left, I would say this is an answer of 196,101. Reminds me of Dalmatians. So I believe this is the answer we're looking for, 196,101. I am going to check it using the algorithm. Some of you call this turtle head method. Thank you, elementary teachers, for talking to them about turtles and the different ways that they turn. So if you know turtle head method, it's kind of this idea where you would take the first digit, the neck of the turtle, times everything up top. So let's try that first and just see if the algorithm gets us the same result. 7 times 3 is 21. We keep the 1 and regroup the 2 to the tens place. 7 times 6 tens gets me 42 tens, plus 2 more gets me 44. I'll keep 4 of those tens and regroup 4. I ended up with, what was that, 44 tens. So I'll keep 4 tens and regroup 4 of them to the hundreds place. 7 times 2 is 14, so that's like 14 hundreds, plus 4 more hundreds, that's 18 hundreds. I'll keep 8 of them here and trade in a group of 1,000 next door. Now I have 7 times 7, which is 49, or 49,000, and I have to add one more 1,000 to it, so I'm going to end up with 50,000. 50,841. That's from the first step of our turtle head method, also known as the algorithm. The next step I've had students try to show me involves the turtle kind of turning his head. So next we're going to deal with this 2 times everything up top. So this 2 is actually in the tens place if you notice. For that reason, the turtle likes to lay an egg. That's what I've been told. Or you can move over a place value. Oftentimes call this Bob. But you know from my other videos that I love 0, so I guess I could give it a special name. Bob, there you are. Next we'll multiply. 20 times 3 gets me 60. So I'm going to put the 6 in the tens place because right now it looks like 60, doesn't it? Next I'm going to multiply 20 times 60. Well, 2 times 6 is 12, and it's going to land in the hundreds place because I'm moving over another place value. So we said we're going to get 1,200. Well, I usually keep the 2 in the hundreds place and I regroup 1 to the next place value. So next I'm taking 20, or 2 in the tens place, times 2 in the hundreds place. Well, 2 times 2 there is 4, plus 1 more gets me 5. I'm going to end up with 5,000. Because again, everything got bumped over, kind of using that place value. That turtle has just moved over a little bit, hasn't he? Okay. Next we have 2 times 7 gets me 14. But really that's 14 way out here, isn't it? It's like saying 20 times 7,000 gets me 140,000, doesn't it? So I'm getting that 14 here for sure, but I want to make sure that I land in the that 14 in front of, or to start in the 100,000s place. Next, I'm going to add these together. So this is again kind of that idea of we had partial products. Okay, we need to now find a total sum. So we're going to take 0 plus 1 to get 1. 4 plus 6 in the tens place gets me 10 tens, but that's really the same as 100, isn't it? So I'm going to regroup here. Keep the 0, regroup the 1. 8 plus 2 is 10, plus 1 more makes 11, 11 hundreds. Well, we'll keep one of those hundreds, but trade one of them in for 1,000. 1 plus 0 plus 5 gets me 6, 6 in the thousands place. 5 plus 4 gets me 9, and 1 plus nothing. Some people like to put Bob right here also. He's got a twin apparently. Gets me just that 1 in the 100,000s place. I do want to compare my answers. I hope we're right. We'll move over 1, 2, 3 hops to the left to give our comma, our notation to help us read this number. It looks like 196,101. Same result, whether I use this area model, which wasn't exactly drawn to scale, or whether I used the algorithm. Some of you like to call that turtle head method. Moving along, we're going to take a look at the third problem here. This one involves a fraction, and it's a word problem. And I do want you to remember that if they give you words, you should give them words back. So here it says there are 6/8 of a cake left over after a birthday party. How many 1/4 or 1/4 pieces can be made from the leftover cake? Ooh, I don't know about you, but cake at a birthday party sounds pretty awesome. And sometimes there are leftovers if you get lucky. Probably if I made the cake, the whole thing would be left. I'd probably burn it or something. But regardless, we will pretend that the cake was delicious and there's 6/8 of it left over. 6/8 left over. Then I'm going to try to break it into as many quarter-sized pieces as I can. So let's go ahead and see if we can draw our 6/8 real quick of a cake. That denominator is really telling me break it into 8 parts. It started with 8 slices maybe. 1, 2, 3, 4, 5, 6, 7 lines should get me 8 parts. Let's check it. 1, 2, 3, 4, 5, 6, 7, 8 pieces to start with. But how many are remaining? Well, you look at the numerator and say just 6 of them. So we'll just shade in 6. This is the cake that's remaining, isn't it? But now I'm trying to break it into 1/4 each serving is going to be 1/4 or 1/4 of the size. So I'm comparing that to the original. So if I look again at the original bar, making this about the same size, again using a comparison model, I'm going to talk about how many fourths I could make in here out of the leftover cake. So instead of bringing down every line, that would get me 8 equal parts. I only need to bring down half of those. I only want 4 equal parts. So skip this one, bring this one down. Skip this one, draw this line in. Skip this one, bring this line down. And if you check, we should have 1, 2, 3, 4 equal parts. Well, the question is here, how many of these fourths, trying to make 1/4 for a serving size, can I get out of the leftover cake? Well, if we kind of continue this idea, and sometimes I will draw a dotted line here in my comparison model, do you notice that I could make 1/4 out of 2 of these 8s? So could I do it again here? Could I take 2 of those 8s and make another 4th? Looks like. So here I have one group of 1/4. I have 2 servings of 1/4. Could I do it again? Absolutely. I have 2 more 8s to make another 4th, another serving of 1/4. Makes 3 servings. And I could do it again if this cake were still here, but someone ate that yesterday. So that's already gone. Nothing more to compare, nothing more to group. I end up getting how many servings? 3. And in this case, I guess they didn't say servings. They said how many 1/4 pieces or 1/4 size pieces. So we want to answer 3 pieces. The good news is it looks like everyone got 2 tiny pieces of cake. So they got a little bit more in each serving. This next problem is a lot like it. They tell us that we're going to draw a model to represent a fraction division, and that's exactly what we did, but this one is minus the word problem. So this is just, again, taking one fraction, dividing it by another, and they do encourage us to draw a model. So let's start that way. To do a division of fractions problem, I usually draw one bar, and that's kind of how I start, and I'm just going to model the first fraction 1/2. Well, that means it's split into 2 equal parts because the denominator is a 2, and I only have one of them remaining, or one of them shaded in. Next it says I want to group them into 8ths instead. I don't want halves anymore. I want to change the size into 8ths. So to do that, I'm going to end up making this a lot smaller. Some people will do that in the same bar. Some people will draw a second bar to do that. So I will just do that comparison bar model that I showed you a moment ago. The second fraction calls for 8ths. So remember, I need 7 lines to do that. Or I could kind of use this as a clue. Do you remember this halfway mark in the first bar? I could split half here. How many parts would I need on either side to have a total of 8 parts? Hopefully you're thinking of a number plus itself, or doubled. That would get me 8, and the answer would be 4. 4 to either side. So I'm going to draw 1, 2, 3 sections, and 1, 2, 3 sections. And when I do that, I end up with 1, 2, 3, 4 parts to the left, and 1, 2, 3, 4 parts to the right. That's a total of 8. Now I have my 8ths. Well, how many 8ths am I trying to put together? What does it say I'm trying to do? So next I'd look at the numerator and say, oh, I want to make a group of 2. 2 8ths every time. So I'm looking for something about this size. 1, 2 8ths. And I'm comparing it to this fraction up above. So again, using maybe this dotted line idea, karate chopping your comparison model. Oh, I could take that 1/2 that I started with and chop it right about there, and I could make one group of 2 8ths. Could I do it again? Could I polka dot, do that right here? Those 2 8ths would take up this next piece from the 1/2, wouldn't it? I would end up with a second serving, or a second equal part. So in this case, when I took the 1/2 and I split it into groups of 2 8ths, I was able to make 2 groups of 2 8ths. The answer is just 2. Now some of you have learned a trick. It really is a trick called freeze, change, flip. It's a mnemonic. It's a way to remember checking your division of fractions strategy to see if it worked. It really shows kind of what we did here, or will reflect what we did here. We should get the same result. So we would freeze the first fraction or keep it the same. Next we would change from division to multiplication. and we would flip the second fraction, also known as multiply by the reciprocal. Oops, I just did it wrong though. So let me show that again. The 8 that was in the denominator moves to the numerator, and the 2 that was in the numerator moves to the denominator, and I'm really ready to multiply. Well, when you're multiplying fractions, you have some options. Oftentimes we'll move straight across, and other times we'll notice some cross simplifying. So for today, I think early in the year, I will just multiply across and see what you notice. 1 times 8 in the numerator gets me 8, and 2 times 2 in the denominator gets me 4. And 8/4 is an improper fraction, but that's okay because I know 4 goes into 8 how many times? The answer would be 2. So oftentimes when the numbers get more challenging and a bar model isn't possible, we will use this idea of multiplying by the reciprocal or freeze change flip. On the next side of your Bellwork, there is a problem that asks you to find the quotient. So we're looking at a long division problem in this situation, which usually involves us using the algorithm. There is a mnemonic that we have talked about at school a little bit, which we oftentimes use: does McDonald's serve cheeseburgers? And the reason why we say this silly mnemonic is because it helps us remember the steps of long division. First we divide, then we multiply, next we subtract, we will check the divisor compared to what is left over, and when possible, we'll bring something down and keep on dividing. So let's go ahead and take a look at this problem and see how we would get started. The first thing I would say is, does 16 go into 8,000? If I have 8 in the thousands place, could I get 16 groups of that? Could I get 16 groups of 1,000? The answer is not very nicely, right? So I would put a 0 up top saying, hey, I did try. Next, I could move over and I could say, well, what if we treated this like 8,800 or 8,800? Or some people will cover up the back of it and just say, what if this was 88? How many groups of 16 go into the 88? Well, you could probably check your multiplication chart. I don't have one in front of me, so I'm just thinking out loud here for a quick minute. I'm thinking that I could take this times 5. That would be 5 times 10 is 50. 5 times 6 is 30 more. That would get me 80. That's pretty darn close, I think. So I'm going to put a 5 up top, and I'm going to, again, just rehearse this mental math with you. 5 times 10 is 50. 5 times 6 is 30 more. 50 and 30 gets me 80, and I'm going to subtract. When I subtract, there is 8 remaining in the hundreds place. And I know that makes good sense. This 8 is smaller than the 16 in the divisor, so I know things are going well. In fact, I've done several of these steps already. First I divided. Next I had to multiply to get that 80. Next I subtracted. 88, take away 80 gets me the 8 left over. Some people like that 0 up front, which is okay too. And I did check. I checked to make sure that if I have 8 left over in this hundreds place, that I couldn't take 16 hundreds away from it nicely. And I can't. Not very easily, right? Unless I want to get something smaller like a decimal or a fraction. So the next step here would tell us after the check, bring something down if you can. And in this case, I absolutely can. I can bring down another 8. Here I have 88 again, but this time it's 88, well, it's 880. I'm trying really hard to think about the place value out loud for you, and that's really challenging for me because that's not the way I learned it. So it would be 88 tens, right? 88 tens, because it's kind of like multiplying that times 10, or 880. Well, I'd say to you, I wonder how many times 16 goes into that. Can I take groups of 16 out of this? And if so, how many groups can I make? Well, hopefully you notice up top we used a 5 before and it worked really well when we had 88. And I said 5 times 16 before got me 80. We could probably use that same multiplication this time and subtract. When I subtract, I'm left with 8 again. And I check. Of course, it's looking like my leftovers are smaller than my divisor, which is a good sign. It shows me that I took out as many groups as possible. And next I'll bring down the next place value. So now I really have a true 88. It lands here in the ones place. And I know 16 goes into that 88 about 5 times. 5 times 16 is 80, and when I subtract, I should be left with 8 again. At this moment, it would be really great to give me an exact answer. It would be fine to write this as a mixed number or something we've been practicing a little bit lately. So I would start at the top and I would write this as my whole number. I get 555. And near the bottom, I get my numerator. So I see that there are 8 leftover pieces. out of the groups of 16 I was trying to build. So if I were to read this, I would say 555 and 8/16. Not a bad answer, but it could be simplified. Do you notice that 8 is half of 16? I can actually divide both the top and the bottom of this fraction by the same common factor. The greatest common factor that goes into both is 8. So when I do that, I end up with 8 divided by 8 gets me 1, and 8 goes into 16 twice. And this whole number comes along for the ride. No one wants to lose 555 of something. That'd be an awful lot. And this could be our final answer. Someone else out there might notice, hey, I could have done another place value. I could have put a decimal behind the whole number and placed a 0 in the tens place, brought down another place value, and divided one more time, and you would have had a final answer in decimal form. So maybe you're a person that did that or even tried it in a calculator. You might have an answer of 555 and 5/10, or 555.5. We have a few decimal problems to look at next. So the next one I see says find the sum. Hopefully you're remembering back to your decimal rules. This is really a problem that comes from maybe 3rd or 4th grade math that you've seen before, where we get to add decimals, which means we have to line up our place values. We have to line up those decimals. So I always do that first. That's my first move. From this first number, I see that there's a number ahead of my decimal. It's in the ones place, and 2 numbers behind the decimal, in the tenths and the hundredths place. From the next number, I see that I have a 1 in the ones place and a 6 in the tenths place. And I don't really want to rearrange them. I want to make sure that they're sitting as close to the decimal as they started. But I will say this, before I can add, I'm a little bit concerned. It looks like not all of these numbers have a pair or a partner or someone to add on to. So do you see something we might want to try? Hopefully you're noticing that we might want to put in a placeholder in the hundreds place. We might want a 0 right here. Oftentimes I say, hey, that looks like Bob. Hi Bob, thanks for your help. The next thing we're ready to do is add up our place values. So we really want to think about adding those little tiny hundredths to little tiny hundredths. So if I have 8 hundredths plus no more hundredths, I still have 8 hundredths. Next I move to the tenths place and I have 8 tenths plus 6 little tenths. Oh, I'd get 14 tenths. But the neat thing is I could keep 4 of those little tenths here and replace one of them or trade it in for one whole. So I'm really doing that regroup, or that, you don't call it that. I'm trying to think of what students often say. Carry. Oftentimes students will say that we're going to carry that one over. Next, my decimal gets to move straight down into my answer. That protects kind of the place values that we've been working with, right? It keeps my whole number separate from the decimal values. So in the ones place, if I have 4 plus 1 plus 1, I'll get a total of 6. It looks like I'll get 6 and 48 hundredths. That makes good sense to me. When I see these decimal problems, I like you to do some quick mental math. This 4.88, this 4 and 88 hundredths really looks close to 5 to me, almost like $5. And this 1.6, it's kind of close to 2, isn't it? So I'm just thinking to myself, what is 1 plus, or sorry, I made that up. What is 5 plus 2? And the answer here would be 7. So this is just an estimation strategy. So I can look at my answer and say, is it close to 7? The answer is yes, and that also helps me know that I placed my decimal correctly. All right, one more decimal problem coming at us. It says find the difference. Well, some students get hung up on this word difference, but what does it look like we're going to do? We're just going to subtract. The difference is just a word meaning let's find the result from a subtraction. Let's go ahead and rewrite this. I like to stack these numbers. Again, I have to make sure that my decimals are aligned. So if I copy down the first number the way it's given, right underneath it, I need to make sure I show the second decimal. And what's ahead of that decimal? A 2. What's behind that decimal? A 3, 5, 9. And I want to make sure I show myself that I'm subtracting this time around. Do you see any places where we might need Bob's help? Maybe we should fill in a place value. Maybe we should put in a placeholder. Maybe you're noticing that underneath the 7, we could really use Bob. Maybe we could use a placeholder there. All right, let's get ready for our subtraction. If we take a look at the typical algorithm, we go to the farthest right column and we say 0 take away 9, and your teachers sometimes say, don't do that, you can't do that. Technically you could, but you'd get a negative. So instead of getting negatives, we decide to go to the neighbor's house. We decide to regroup. We go to the 2 and leave him with 1 group instead. And what he's just shared with us, we break into 10 little parts. So we have 10 little units to work with. 10 minus 9 gets me 1. 1 over here in the thousands place. Next I move to the hundredths place, and I have 100 take away 500ths, which you could do, but it wouldn't be a lot of fun with those negatives before we learn them. So instead we usually go to a regrouping strategy. We go to the tens place. We'll leave him with 0, and we say thank you for the group of 10, which we add here. 10 plus 1 gets me 11. Well, 11 hundredths take away 5 hundredths gets me 6 hundredths. And now I take a look here at the tens place, and I have 0 tenths take away 3 tenths, which is possible, by the way, because you're learning about negative numbers right now in 6th grade math. But it wouldn't be very fun to have all these negatives mixed in at this moment. So I think my suggestion would be, let's go make this a larger group to work with. So we go to the neighbor, we take from the ones place, leave him with 0 ones, and the group that he just gave us, we break into 10 little tiny pieces. We now have 10 tenths. Take away 3 tenths. Gets us 7 tenths. That decimal, if you remember, comes straight down. Helps us keep our place values separated from the decimal parts and the whole number. Now I have in the ones place 0 ones, take away 2 ones, and holy regrouping Batman. We've had a lot of this, right? While you can take 2 away from 0 and get negative 2s, I'm not sure how we'd record that here right now. So in the algorithm, we do a regrouping strategy. We go to the next place value. We change it to 1 smaller than what they had, so we'll leave him with 6. And we break what he shared with us into 10 tiny little units. 10 tiny little units, take away 2 units, leaves me with 8. Next I have 6 in the tens place. Take away 0 tens gets me 6 tens. This is the final answer. There was a lot of regrouping in that. I'm wondering if there might be a better way for us to set that one up and model it for you. At the moment, I'm not sure I have a second strategy. I'm going to think on that. This is a good final answer, but I noticed that we had not only 1, 2, 3, 4 regroups, we had a lot to keep track of as far as when to regroup and when that was happening. Let's move ahead to the last problem. I think it's the last one, which asks for the GCF. And if you remember from last week, and also from your recent unit test, GCF stands for greatest common factor. Oh, there's more than one left. Okay. Greatest common factor really means the biggest number that divides into both of these. So I'm trying to break them into factors. Well, there are lots of ways to do it. Your poor teacher loves rainbows. I hate rainbows. Your teacher right now, Mrs. Schumann, kind of loves T-charts, I'll be honest, but you have to be careful with them. The other option is trees. I will try T-charts just because I don't think these numbers are too outlandish. I think they're things that we will find on our multiplication chart or we might be very familiar with. So let's start with the smallest and the largest factors of 24. Well, I know 1 times 24 gets me 24. Cha-ching. Will 2 work for this number? Does 2 divide nicely into 24? Or does 2 multiply by something nicely to get me 24? The answer is yes. 2 times 12. Does 3 go into this number? You could check the 3 row on your multiplication chart, or you could say, hey, if I add the digits together, could I divide that by 3? The answer is yes. 2 plus 4 is 6. That divides nicely by 3, so this number will also. 3 times something is 24. 3 times 8 is 24. Next, we ask ourselves, should we try 4? And my hint for 4s is this. If 2 works and you're left with an even number over here, 4 should also work. So I do believe this is in the 4 row. I want you to check it out. 4 times something is 24. We could count by 4s. We could say 4, 8, 12, 16, 20, 24. How many times was that? That was 6. I counted 4 6 times. 4 times 6 is 24. The only number I'm missing between 4 and 6 is 5, and I know 5 is not a good factor because this number doesn't end in 5 or 0. So I have my factor T-chart complete. Let's look at 40. Well, I know the smallest number for all numbers on the planet. The smallest factor that will work for all of them is 1, and the largest in this case is 40, the number itself. Is 40 even? If you recognize that it is because it ends in 0, we know 2 will work. 2 times something is 40. So I could go across the 2 row and I could find that 40 and say 2 times 20 is 40. Will 3 work? If I add the digits together, do they divide nicely by 3? I hope you're saying no. That's not going to work very nicely, so let's skip the 3 row. Next, we'll check the 4 row, and if you remember, my trick for 4s is this. I look at the 2's and see next door if that number that I had is even. If it is, I know I can bump this one up and chop this one in half. I can double the 2 and I can halve the 20. So 4 times something is 20. No, 4 times something is 40, and the answer is 10. 4 times 10. Notice again, as this one went up, I doubled it, and this one went down, I chopped it in half. That happened over here also, if you notice. I doubled it, I chopped it in half. Kind of has that inverse relationship, that opposite going on. All right, next I'd say to you, should we check 5s? And I hope you'd say yes, that thing ends in a 0. 5 should work. 5 times what? And I hope you'd say 5 times 8 would work. 5 times 8 is 40. I need to check 6 and 7 because I'm missing them in between these two numbers on my T-chart. And 6 and 7, checking your charts, they're not going to do it, are they? So next I'm circling anything that I see they have in common. Looks like we have common 1s. Yay, we share a common factor of 1. Ooh, we share a common factor of 2. Do we share anything bigger than 2? Oh, we share a common factor of 4. But is there anything greater than 4? Oh, we have a common factor of 8. Are we getting there? In fact, if you do any more comparing, you'll see the largest number that they both have in common is 8. That means that both of these numbers would divide by 8 if we had to do it. If we had to simplify a fraction, that would be our greatest common factor that would get us there quick. So the GCF, greatest common factor, the greatest number that divides into both nicely, is 8. That takes us to our last problem today, which talks about LCM. So it says, Maggie says the LCM of 8 and 12 is 24. Her friend Glenn says the answer is 4. Who is right? Explain. I'll be honest, if you know the meaning of LCM and you remember what strategy we use, when I see this LCM, the M, which reminds me to multiply, I'm pretty sure I know who's right already. I'm pretty sure the numbers are going to have to grow, but I probably need to prove it. It says, who is right? Let's explain. Well, if you look back at our recent test or you think back to your notes packet, sometimes when I'm looking for an LCM, I can do exactly what it's hinting at. Multiply. Why don't we take the two numbers we're given, 8 and 12, and write out their multiples. So we're going to test this out. Multiples usually mean more. So when I'm talking about whole numbers and I multiply, I'm going to get something more. 8 times 1 is 8. 8 times 2 is 16. 8 times 3 is 24. Hey, I got one of the things they mentioned. I just got 24. But I have to try that also with 12 and see if it's going to check out. So I could count by 12s right now. Skip counting. 12, 24, 30. Oh, I don't have to do 36 because I noticed something. I just got 24 again. When I write out my multiples, that again is what the strategy is. It's a list of multiples. I get 24 both times. So my question is this. What is Glenn thinking? Where did Glenn get this 4 from? Maybe 4 is something else. 4 is smaller than 8 and 12. Maybe 4 is something more like a number that I could use to divide into or to get 8 and 12. Maybe 4 is more like a factor. I'm just thinking about that. Maybe 4 is a factor. It looks to me like the LCM is 24. So it says, who is right? Maggie says the LCM is 24. Her friend Glenn says the answer is 4. So why don't we say, we've discovered Maggie is right. The LCM is 24 because multiples get larger, not smaller, like factors do. Maybe there's a better way of writing this out, but I'm thinking to myself, I know factors get smaller. I wonder if I made T-charts for 8 and 12, if I might find a 4 in there somehow. But I know multiples usually mean more. The number's going to grow or multiply. I hope you've made some corrections. I hope you've done some checking. I hope you've added some strategies to your toolbox so you are able to tackle some more problems like this soon in the future. And if you have questions, please bring them ready for class the next time we see you.